Hello, and thank you for joining me today. My name is Simon Byrne. I'm a lead software engineer on the Klima project at Caltech. We're building a next generation climate model called Climate Machine. But today I'm going to be speaking about ClimaCore, which is a suite of tools we've built for constructing spatial discretizations. Now, these are primarily aimed at climate and weather models. Their initial aim is supporting spectral element discretizations in the horizontal and staggered finite difference discretizations in the vertical. It's currently under active development, but I'm going to give you a little overview of how it can be used today. So firstly, we load the package along with some extra ones which we use for useful utilities. The first piece you need to define is a domain. Now this represents a region of space, so in this case, a rectangular domain that is periodic in both directions. From that, we construct a mesh, which is a division of a domain into elements. So here is 16 by 16 elements, so 256 total elements. A topology on that mesh then describes the ordering and the connections between the elements of the mesh. And from that, finally, we get to a space. So a space represents the function space which we're discretizing. So in this case, the key ingredients here are the topology as well as a quadrature rule, which determines where to place the individual nodes within that element. So here we're using Gauss-Lobato-Legendre quadrature, which uses 4 nodes in each direction, so 16 nodes per element. And then from that, we can construct a field. Now, a field is a function that is defined on a space and is represented by values that are stored at each node. The simplest such field is the coordinate field. So this is a struct valued field with names x1 and x2. And we can access for a struct value field, you can access component fields via the get property overloading. So here we can access the x1 field, which is now a scalar field. Broadcasting can be used to define new fields from existing ones. So here we apply the sinusoid of the x1 coordinate to define our resulting field. Of course, for these sorts of objects, it's very useful to be able to plot them. So using plot recipes, we are able to visualize especially two-dimensional fields quite easily. For those of you who don't want to use a GUI or are working on clusters or other remote computers, it's very useful to be able to use Unicode plots. So similar operations work for those as well. Well, unfortunately, it doesn't quite render correctly in the Jupyter output. The analogous reduction operators are defined in a consistent way that's consistent with the fields being functions. So for example, a sum will give you an integral over the domain. And since this is a sinusoid, it integrates to 0. And a norm will give you the L2 norm over the domain. So the key thing when using PDEs are operators. So these operators here are spatial derivative operations. And one of the key requirements is that we need to be able, for performance, is that we need to be able to fuse multiple operators and functions together in one go. Now, fortunately, Julia provides exactly what we need for this. It's called broadcasting. So when you do use the dot overloading, use dots with multiple functions, it will fuse all those operations together into one expression and to avoid allocating intermediate arrays. Unfortunately, due to it has a very nicely designed API that we are able to extend and use well beyond what it was originally designed for. So operators here are what I've termed pseudo functions, in that they can't be called directly, but they operate like functions when used in the context of broadcasting. So for example, to take a gradient, we extract the gradient operator. We apply that operator dotted over the field, and then we can plot the result by plotting the first component of the gradient. So as you expect, this gives you a cosine field. If we then take the divergence of that, i.e. the divergence of a gradient being a Laplacian, we were able to fuse those operations into one pass, which gives you the negative sinusoid. Now, of course, the whole point of this is to be able to solve partial differential equations. And the field abstraction plays nicely with the ordinary differential equations solvers from the SciML ecosystem, in that you can use it as a state variable and generally works with most of the ordinary differential equation solvers that are supplied. So for example, consider a continuous Galerkin approximation to the heat equation. So here is the tendency of y is defined as the Laplacian times some constant. The key constraint here is that we do this by first taking a gradient and then applying what's called a weak divergence. So this is applied by obtained by taking the product rule, and then composing those to obtain your tendency dy. The continuous Galerkin approximation requires that the function space be continuous. So the next step this is followed by a direct stiffness summation, which projects the discontinuous field back into the continuous domain. And we can plot the results of that. So this dissipates the sinusoid as you would expect. So next we solve the shallow water equations. This is a more complicated set of equations, in particular they're nonlinear. And to avoid numerical problems, we use overintegration, which means that we evaluate the flux and compute the operators on a higher order mesh. In this case, we are using seventh order, using 7 Gauss-Legendre-Lobato points in each direction. So firstly, we initialize our state. And here is a plot of our initial tracer field that we'll visualize. And now we define our flux function. So as you can see, our flux function looks very similar to the corresponding equations we wrote. And here we have an additional operator as being an interpolate operator, which interpolates the higher order mesh, and then a restrict, which projects back down to the lower order space. We combine these, again, using an order differential equation solver. We're able to solve this. So thank you for joining me today. I hope you find these tools useful, and we'd love to hear your feedback.